Hello, this is Professor Dan Kernler of Elgin Community College. This is another video in my statistics series. This video is all about different ways of counting. You'll see. So what we're really talking about in this video is different ways of counting how many ways something can happen. I like to start this with a really simple example. So suppose you want to create a tux and you're looking at different options. Got different jackets, maybe a couple different jackets, couple different vests, maybe 3 different colored shirts or styles of shirts. You want to know how many different possible options are there. Well, in this case, you got 2 different jackets. You have 2 different types of vests for each type of jacket. And then for each of those 2 combinations, you have 3 different shirts. So you end up with 12 different combinations. And the key is if we focus on what happened here to think about a generalized way to do this, we have the total choices. We have 2 jackets, 2 vests, 3 different types of shirts. We multiply all of those together to get the 12 total options. So this is the key here, is we are multiplying the number of ways to make each choice. If we wanted to generalize this, say we have choice 1, there's n sub 1 ways to do that, choice 2, n sub 2, choice 3, n sub 3, etc. Then the total number of possibilities you would just multiply, n1 times n2 times n3, etc. All right. Let's suppose we're trying to write a password. It has 5 characters in it. We have some rules. These are kind of funky rules. The first has to be a capital letter. The second 3 have to all be digits 0 through 9, but we can't have any repeats. And then the last one has to be some kind of symbol, say one of these 4 symbols. Question is, how many possible passwords are there? Well, what we're going to do is we're going to count the number of ways to do each step, and then we'll multiply them all together. So we have 26 capital letters. For the digits, well, there's 10 digits, so there's 10 choices there, but we can't have any repeats. So let's say we choose 2, for example, then there's only 9 left, right? And let's say the next one chosen is 4, then there's only 8 left for the third one. So we've reduced the number of options for each one. Then for the symbols, we have 4 different symbols. If we multiply all of those together to get the total, we get 74,880 possible passwords. The key here again is we're multiplying the number of ways to do each part of the process. What about like a passcode for a door? We say it's supposed to be 4 digits and we can't have any repeats. So there's 10 choices for the first one, then 9, then 8, then 7. Multiply those together. There's 5,040 possible codes. Now, this process of 10 times 9 times 8 times 7 occurs often enough that there's value in developing a shorthand for it and a formula, because it does occur very frequently where we have 10 digits in this case and we want to order 4 of them. So let's dive in on these and focus on this 10 times 9 times 8 times 7 a little bit deeper. This is called a permutation. Specifically, this is when you arrange our objects, you arrange them, which means order does matter, chosen from n total distinct objects. So we had the 10 distinct digits, 0 through 9, and then we want to arrange 4 of them. And it's a password, it's a code, so the order does matter. We're arranging them. The formula that we're going to use for this uses 10 with an exclamation point. Now, this doesn't mean like a really big 10. No. What it means is 10 factorial, which is 10 times 9 times 8 times 7, etc., down to 1. So if we look at our 10 times 9 times 8 times 7, what if we just multiply by all of them all the way down and then divide by the ones we don't need? So that would simplify and give us the 10 times 9 times 8 times 7. Well, if we look at this expression, this is really 10 factorial in the numerator and then 6 factorial in the denominator. Now, we know the 10 comes from the 10 digits, but the question is, what about the 6? Well, that's the leftover, right? So if you look at that 6, it's really 10 minus 4 factorial. And so we have this 10 factorial over 10 minus 4 factorial. If we generalize this, the 4 is the number of objects we're choosing, and then the 10 is the total number of objects that we're picking them from. So we have this formula then, we could say n factorial over n minus r factorial. And this is called a permutation, sometimes written NPR, the permutation of R objects chosen from N. All right, next topic here. What if we have a group of 125 people? We want to know how many ways can we just pick 4 of them to be on some kind of committee. So we've got all these different possible groups, but we don't care what order they're in. So this is a slightly different question. We're going to start it the same way. We've got 4 spots. So we could do a permutation, 125 times 124 times 123 times 122. The problem is, this assumes that the order of them matters. So what we want to do is we really want to divide by the number of ways that those 4 people can be ordered. Let's say we have these 4 right here. Well, there's 4 choices for the first person. Then there's only 3 choices for the second person. Then 2, then 1. All right, let's expand this to try to develop a formula for this one too. We could multiply the rest of them in the numerator, so we could multiply by 121 factorial, and let's do the same in the denominator, 121 factorial, so we're really just leaving it the same. Seems like it's making it more complicated, but now the numerator is all the way from 125 all the way down. So we could write the numerator as 125 factorial. The denominator has a 4 factorial in it. So now the question is, where do these numbers come from? The 125 is just everybody. Then the 4, those are the 4 in our group. And then the 121 is really everybody else. We could really write it as 125 minus 4. So we have a formula when simplified that looks like this. Let's kind of focus on that and try to develop a generalized version like we did for permutations. This one is called a combination. What we're doing here is we're choosing our objects. We're not arranging this time. We're just choosing them from n distinct objects. And again, the key here is without regard to order. Now, in terms of the formula, the 4 is what we're choosing. That's how many we're going to pick. And then the 125 is the total n. And so we can have a simplified formula, just kind of generalized in terms of n and r, that looks like this. We usually use NCR for this to denote a combination. N factorial over r factorial times n minus r factorial. So the 2 that we've done so far, permutation, this is when we're arranging our objects from n distinct objects, and we get NPR equals n factorial over n minus r factorial. And then combination, this one is we're choosing our objects from n without regard to order. This is NCR, that's n factorial over r factorial times n minus r factorial. All right, the next one is kind of a silly one, not used as often, but it's kind of interesting. So suppose we take the word statistics, and we're wondering how many ways can we reorder those letters? Now, we're not reordering them into real words, but how many ways could we reorder them? Now, here's what's different. We're ordering all of them, but they're not distinct. So how many ways can we order objects if they're not all distinct? Let's pull these letters down and investigate it. We've got 10 spots. What we could do is we could take those 10 spots and choose 3 of them to place the 3 T's. So we have 10 spots. We're going to choose 3 of them. Now, where the 3 T's are, it doesn't matter what order the T's are because they're just T's. That's why this is a combination. So we're going to choose 3 spots out of the 10 to be the T's. Let's say it ends up here. Okay. Now, we have 7 spots left. From those 7, let's choose 3 spots to put the S's. Okay. How many spots? See, 7 minus 3. Okay, there's 4 spots left. From those 4, we want to choose 2 to put the I's. And then from the 2 remaining, we want to choose 1 to put the A. Now really that's just, there's 2 choices there, but we're going to follow the pattern here, 2C1. And then lastly, 1C1. From the 1 remaining spot, we want to choose 1 spot for it. So that's the C. We're going to try to use this kind of silly example to generalize a formula. So let's look at all these combinations and let's write them all out using their formula. So 10C3, 10 factorial over 3 times 7 factorial. Similarly for 7C3, 4C2, 2C1, and then 1C1. There's a lot of simplifying here. 7 factorials, 4 factorials, 2 factorials, 1 factorials. In fact, 0 factorial is by definition 1. We're not going to get into the reason why, but that is a definition. 0 factorial is 1. And so now we actually just have 10 factorial over 3 factorial, 3 factorial, 2 factorial, 1 factorial, 1 factorial. If you think about where these all came from, that's from the 3 T's, 3 S's, what else was in there? 2 I's, an A, and what else was there? A C? So in general, you have the total n factorial, and then you divide by the factorial for how many there are of each type. And this is a permutation, so it's an ordering of non-distinct objects. And this is assuming here there's n total, and then n1 of the first type, n2 of the second type, etc. Now, that is admittedly not a very commonly used one, but it is kind of interesting and one to just kind of add to your tool bag. The permutations and combinations are definitely much more common. All right, that is it for this video. That's some different counting techniques. Hope you found this interesting. If you're interested in seeing more of these, you can subscribe, hit the bell to get notified. There's a whole series of these coming out. Also, thank you to the Elgin Community College Board of Trustees who approved my sabbatical during the spring 2021 semester, and that's what gave me the time to record, edit, and produce and upload all of these videos. So thank you so much for watching, and I will see you in the next one.